Okay, class, welcome back. Hey, it's Tie-Dye Friday. Okay. Here's where we left off with our problem. Okay, just a reminder. We were given this as the normal, like resting heart rate for people, 74.52. Okay, and what we're going to do is we're going to show 10 people a movie with a fast-paced soundtrack. And the question I'm asking here in this research project is whether or not having them listen to this soundtrack will affect their heart rate. Step one, we've done this before, okay? The soundtrack, if it looks like normal, right, 74.52, calling this the null hypothesis. If the soundtrack has no effect, and then our alternative hypothesis is that playing the soundtrack is going to change heart rate to something other than normal, okay? And in this case, the soundtrack will make the heart rate something different than 74.52. Step two, so this is step one, right, of our hypothesis testing. Step two then is to set up our criteria for making our decision. We're going to use an alpha level of 0.05, okay? We need to identify the critical value for t. This is analogous, like the critical value of 1.96. We need to adjust it a little bit. For 9 degrees of freedom, we have 10 people, so we have 9 degrees of freedom here. Then our critical value is 2.262. Okay? And for this problem, we need to do a t-test. So I'm going to go back over here, and I'm going to show you how to do this, I think in the simplest way. We have our t. We're going to get the mean for our soundtrack group. We're going to compare that to what we see normally for groups of 10. We're going to use S sub m as our denominator. And so what we're going to do here, my Matryoshka dolls are in my office, and I can't go to my office, but if you know what a Matryoshka doll is, it's those Russian dolls where there's a little one and a bigger one and a bigger and a bigger and a bigger. You sort of put those together. This is what I'm going to do, or this is how I think about it in my head when I do a t-test like this. So let's look at these symbols, right? And by the way, if you can look at this formula and understand these symbols, I just want to remind you how far you've come in one semester. Because again, it's time to give ourselves a little bit of a pat on the back. If I were to put this up in the first week of classes, yikes, you might have been really intimidated by what you see. But you're good, whether you realize it or not. This is like a z, right? The z had the mean of the sample compared to the mean for the population, but we were given this standard deviation. In this case, we need to guess at it. So what does this have to do with Matryoshka dolls, right? Well, listen, here's the big formula, but here's what we need to do. I know that this is the mean for the sample, and by the way, did you guys calculate the mean? The mean for the sample was 82.00. We're going to compare that to 74.52. We're going to compare 82 to 74.52. I mean, that's the very essence of our research question. When I look at a group of 10 people that watch this movie, here's the mean. How does that compare to what I see normally? That's the essence of our question. There it is, in the numerator, okay? But I need to take into consideration this measure of variability. So this is sort of the new thing, and I'm going to unpack this Matryoshka doll a little bit. I'm going to unpack it. So, I mean, I give these formulas when I give the exam. So you just need to sort of unpack it, pack it up, unpack it, okay? So what is S sub m? Well, that's equal to S divided by the square root of n, okay? All right, well, I know n is the sample size, okay? But what is S? S in this case is the sum of squares divided by degrees of freedom. Take the square root, remember. And now all I need to do is get my sum of squares. All these equations are given. So if I get this, and you better be able to do this, okay, we've done it lots. If I get this, then I plug this number into here. Once I get this, I plug this number into here. Once I get this, I plug that number into here. Okay? So let's do it. Were you guys able to get the sum of squares? In the sum of squares, where is it? Well, 6, 7, I'll give you all the numbers just so you can check. You should be able to do this. If not, you need to go back and practice, right? So it's 6, 7, 5, 5, 8, minus 6, 7, 2, 4, 0. So the sum of squares is 318. Okay, those are the values for each of these. Square each number, then add those together, minus this, you're adding all the numbers up first, squaring, divided by 10. Okay, so here's our sum of squares. All right, good to go. 318 divided by the degrees of freedom now is 9, because we have 10 people in our study. Don't forget to take the square root. Okay. And so that is equal to 5.94. And I'm going to go through and talk about what these numbers represent conceptually. Okay. Talk about what these numbers represent conceptually in a minute. Once I have this S, then I can go up here and say 5.94 divided by the square root of 10. See how easy it is to make a mistake? Because this is n. Keep your wits about you. This is degrees of freedom. I'm saying keep my wits about me too, right? Degrees of freedom, this is n. We have 10 people in our study. And so that S sub m is equal to 1.88. Okay. So sum of squares, that Matryoshka doll goes in here. Once you calculate this, this goes here. Once you calculate this, this goes here. So 1.88. Okay. And we have an overall T then, 82.00 minus 74.52 divided by 1.88. And so the T value here is 3.98 for our T. And I'm hoping that when you see a number like that, you're like, wow, that's pretty large. Okay, we're going to compare that to our critical value. But let me go through this, because once you have the formulas, with practice, of course, you can go through and get the values here. But I do want to remind people, because I will be asking this, of course, you need to know the conceptual meaning of these numbers. I'll show you probably the last, well, I don't know if I'll be able to, well, anyway. You're going to do all this on a computer. Boom, boom, boom. It's going to be done quickly, okay? But you need to know the conceptual meaning of each of these. And so let's do this, okay? Of course, this is a measure of variability with our sample, okay? This is sort of the building block. This is S instead of sigma, but remember what S is. S is our guess. S is our guess for sigma. S is our guess for sigma. That is, we're using sample variability to make a guess about the population variability, okay? This is our guess, our unbiased estimate for sigma. That's what we're doing in this step. We're making an unbiased estimate for sigma. This is our central limit theorem step, okay? We've done this before. This is old news, okay? It's just that now it's based on our guess for sigma instead of sigma. Make our guess for sigma, do our central limit theorem. This looks like a z-score, except we're doing it with an estimated value for sigma, okay? Guess for sigma, based on the sample variability. Guess for sigma, using degrees of freedom. Central limit theorem. Here's our t-test, 3.98. And let's go back now. So this is, our scratch sheet for our computations for our statistic. Our observed t is 3.98. We're going to go back here. We're going to compare it to 2.262. This is larger, right? It goes into the tails. It's extreme. And so what are we going to do? What are we going to do in this case? That's right. Of course, we're going to reject the null. And by the way, you don't always reject the null. The data will tell you whether to reject the null or not. If we did this computation and our t-value was, let's say, 1.41, if our t-value was 1.41, we certainly would not reject the null, okay? I like to use examples where we reject the null because it's like, wow, I'm doing this research and it comes out significant. Of course, it's all made up. But we can do an example where we don't reject the null, where we say, hey, the soundtrack didn't do any work or didn't have an effect. In this case, it certainly did, okay? We're going to compare it to this. We reject the null. It appears that the movie soundtrack significantly increased heart rate. T, because I did a t-test, with 9 degrees of freedom, T with 9 degrees of freedom equal to 3.98. 3.98. Wow, the top. Go back here. This difference is almost 4 times the size of the variability. The difference is almost 4 times the size of the variability. That's what this indicates. Difference over variability, difference over variability, difference over variability, okay? Probability that the null is true is less than 5%, okay? Period after the parentheses, okay? I wonder if anybody has any questions, all right? Now, when you read the research literature, sometimes you will see in the parenthetical, you'll see something like T with 9 degrees of freedom, which means that tells me they had 10 subjects in their study. 3.9, P less than 0.05. Sometimes you will see this, and this is a good example here. T with 9 degrees of freedom equals 3.98. This is from the data that we collected, not our criteria. This is from the data that we collected, okay? P less than 0.05. Sometimes you'll see people use, instead of p less than 0.05, they will write p less than 0.01. Okay? And you might think to yourself, what the hell does that mean? Okay, well, let's take a minute and look at our book. Let's look at our book for that critical value again. I'll give you a minute to get your book. It's important that you do this. So I'm looking at the t distribution. I'm looking at table B2. And let's look at our 9 degrees of freedom. Let's look at our 9 degrees of freedom. This is where we got our critical value, okay? Going to go across 2.262, 2.262, okay? Well, if I keep going across that row, I'm going to keep going across that row till I find the column where it says, if you see that, proportion in two tails combined. Everybody see that on the top? Let's go proportion of two tails combined, 0.01. That is 1% instead of 5%. Instead of 5% in the tails, I'm going to put 1% in the tail. And I want to know the t value that would define the extreme 1%. Everybody see it? It's in the very far right column. 9 degrees of freedom. Let's go across to the very right-hand column. And it says 3.25. What that is saying is, if we set up a t distribution, if we go out to the extreme 1%, that would be a t value of 3.250. Everybody see it? Negative 3.2 and positive 3. That's defining the extreme 1%. That defines the 1%, right? Instead of 5% in the tail, we're going to go out even further. Instead of alpha level 0.05, if we're not going to do this for this class, but if we use an alpha level of 0.01, that is, we're not going to reject the null until we're in the extreme 1% of the population, we would have an observed value from our data that is that far out, okay? So some researchers will want to indicate that. And they'll say, listen, our data is so impressive. This is almost 4 standard deviations away, 4 standard errors away. So I'm going to say my probability that the null hypothesis is true is less than 1%. It indicates a little bit more confidence that, yeah, this soundtrack really worked. Now, this is what we're going to do for our class. We're just going to do the 0.05, whether it's greater than or less than 0.05. That's going to be our cutoff. But when you read the research literature, and if you're going to go to graduate school, you're going to read research literature more than you do as an undergraduate. This is the currency of what professionals do, okay? They make their decisions based on data, not based on gut feelings, not based on political bias. They're really going to collect some information and try to make a decision based on that. Of course, we could always be wrong. This is a probability, okay? Scientists are never certain. That's one of the things that's a big surprise when people take this class. I thought you could prove things with statistics. No, but when I say that the probability I'm going to make a mistake is only 1%, oh my God, I wish all of my decisions were, I wish I was that confident in all my decisions, okay? So, that's that. That's our T. So we've done 2. I'm hoping it's making sense. Do some of the problems in the book as well, okay? And try to understand what we're doing here. This is just like a z-score, except for here, okay? We're going to make our guess for sigma. Then we're going to do the same thing we did with the z-score. So this is kind of a 2-step, or 3. I mean, if you want to consider this the first step, the building block. We're going to get our variability for sample, make a guess for sigma. That's this step. Central limit theorem. Instead of individual scores, we're going to do samples. Okay, that's what this is. Building block, make a guess for sigma. Central limit theorem. Put it into a formula where you're looking at the difference over the variability. Difference over variability. Okay. Just to bring home this difference over variability thing, we now have this formula that we used. That's for individual scores. How far away from the mean are you? How different are you? But we have to compare to variability, right? Then we had a z-score for samples. We're going to look at a sample mean. How far away from the mean of all the sample means are you? Divided by the variability of all the sample means. Difference over variability. Difference over variability. Right? And then finally, our t is in the same form. It's the same form, okay? Very powerful. Is our mean for our sample compared to what we see normally divided by standard error, but this is an estimated standard error. We made an estimation based on our sample. Difference over variability. Okay. I hope that when you see it like this, that you see the common feature. Individual score, samples, where you have the sigma, samples where you're guessing at sigma. It's all the same form. Difference over variability, difference over variability, difference over variability. Okay. All right. So let's So I hope this all makes sense. It will take you some time to work through this. Read chapter 9. Remember all the stuff we did in chapter 8. Make sure you read section 4.5 in chapter 4. So the onus is on you now. Work your way through it. Email me if you have questions after you do that stuff. Do some practice problems, okay? But I do want to just start on the next phase, and it builds right on this, okay? Because so far we still are given the mu here, okay? And up here we're given the sigmas. Here we're starting to get away from having to be given information, okay? But we're going to move even further away from that. And I want to talk, I'm just going to introduce this because usually when you do an experiment, when you're doing research, you're not just doing one group. You're actually going to look at two different groups. Okay, most of you are aware of sort of simple scientific method where you have an experimental group and a control group, although I don't typically like that moniker because they're both part of the experiment. But people know a experimental group from a control group, and you're going to compare the two. Okay, so let's do another example. Okay, where I don't really have any information. Okay, let's do this example. And I'm going to set it up, and I'm going to let you guys do some of the computations, and then we'll see how to do the statistical analysis. Let's see. Let's suppose that here's what we'll do. We will have some kind of a product So let's do some advertising. Okay, we'll do some advertising, and we'll do a product. I guess it doesn't really matter what the product is. Should we do? Let's do beer. Okay, I like beer. What is that song? Should I sing it for you guys? I like beer. It makes me a jolly good fellow. Whiskey's too rough. Champagne costs too much. Liquor puts my mouth in gear. Blah, blah, blah. I don't know how the rest of it goes. Anyway, it's an old, goofy-ass song. Let's do a beer commercial. And I wonder if we have a beer, I wonder if a celebrity spokesperson would help me sell my beer versus like a regular Joe or Jane, okay? So I'm really talking here about two groups, okay? So here's, let's do this. Let's do celebrity spokesperson, okay? Everybody with me? And we're going to compare that to average Joe or Jane. Okay. And I'm going to do some focus groups, and I'm going to show them this commercial that I've made, and one of them will have a celebrity spokesperson, and the other one will have an average Joe, okay? And then I'm going to say, let's make the numbers easy in this case too. I'm going to ask people, on a scale from 1 to 10, how likely are you to buy this product, okay? Where 10 would mean I'm more likely to buy the product, and 1 would mean I am not interested in the product, okay? So let's look at the numbers, all right? And we'll do this. We'll do, for the celebrity spokesperson, let's say 4, 6, 2, 7, 9, 5, 1, 2, 3, 4, 5, 6. Yeah, that's okay. All right. I want to make the computations relatively easy. And for the average Joe, the first person says 9, and 8, and 4, and 3, and 7, and 5. Okay. So there are our data. Okay. Now, as you can see, I got no means, that is no mu's, I got no sigmas, I got nothing. But this is my research. I got 6 people in each of these groups. I show them the different commercial. They're exact, the commercials are the same except for, I mean, it's the same script, it's the same product, same lighting, all of that stuff. I'm going to be a good experimenter. That's what a good researcher is. And in fact, which one is the control group and which one is the experimental? I don't know. I mean, maybe this is the control, and then with celebrity is experimental. It doesn't matter what you call it, right? There's 2 groups, and they're each indicating, the people in each of the groups are indicating how much you're going to buy the beer. So there's 6 people in this group. There are 6 people in this group. And again, if I was going to do this research, I'd probably want something more like 50 in each group or 27 in each group or whatever, okay? What is the question? What is the question that we're trying to ask here? Well, can we do this in a null hypothesis and a alternative hypothesis? I mean, what I'm going to do here is I'm going to say, on average, let's call this the mean for the celebrity. Let's call this the mean for Joe, okay? I want to know if there's a difference between these two. Yes? I mean, that is the research question. And if I'm doing this study, I probably have some idea that maybe the celebrity will help me sell this product, right? I got to pay this person a lot of money to endorse my product. And so that's the question that I want to know. Can we put that in symbols? Can we put that in symbols? Let's see if you can write down a null hypothesis in this case and an alternative hypothesis in this case. I mean, I'm going to challenge you to just jot it down. See if you can do a null and an alternative hypothesis here. Everybody got it? What would it look like? Well, the null would say that the mu, and I'm using mu here, this sometimes confuses people because what I'm saying is I'm assuming that there is a hypothetical. It doesn't really exist. This is the first time this is ever done with this product, right? But hypothetically, there's a bag of people who would watch a celebrity selling this product, right? It's hypothetical. It's hypothetically out there, even though it's not really out there. And so I'm going to use the mu as my symbol. The mu for the celebrity, that is the average for how much they are going to buy the product, would be equal to the mu for the Joe group. Okay? That's what I'm saying. There's no difference. And in fact, if I want to sort of say there's no difference, why don't I subtract celebrity and Joe? If there's no difference, this would be 0, right? This is the same as this. If they're equal, when I subtract them, the difference will be 0. Everybody with me? What would the alternative hypothesis look like? Well, what I'm saying there is the celebrity endorsed product, we're going to see different numbers than for the Joe. These numbers represent how likely are you to buy it, right? The higher numbers mean more likely. Okay? Everybody cool? And if these are different, then I should say THEN, then if I subtract them, I'm going to get a value of something other than 0. If they're equal, I'm going to get a value of 0 or something close to it. Remember, this is not arithmetic. It's statistics and probability, okay? If they're equal, when I subtract, I get 0. If they're not equal, then I should get something other than 0. Everybody good with that terminology? Okay. So let's look at the means. Let's get the means here. I'm going to give you a minute, and I need to get my calculator. Let's do this together. Okay. There are 6 in each of the groups. Let's do this. I think I have a mean of 5.50 for this group. Okay. And let's see. And 6.00 for this group. Okay. So I already know that the celebrity is not higher than this. I mean, just from the numbers. But I'm wondering if the average Joe is actually, if this is a meaningful difference, okay? We're not going to do this through opinion. We're going to do a statistical analysis, okay? We're going to do a statistical analysis of this, okay? So I have my means, and I want to see if when I subtract them, it's equal to 0 or not equal to 0, okay? And so here's what we're going to do, folks. The essence of our statistical analyses is difference over variability. Is difference over variability. Okay. We're not given any standard deviation in this case, so we are going to do a t-test. We are going to do a t-test. If we had sigmas, we could do a z, but we don't have sigmas. And I want to show you, or I want to challenge you again. Remember the structure of our statistical test. Difference over variability. Difference over variability, okay? So the essence of our research question is whether or not there's a difference between the two groups, okay? Our other research questions, z-score. The z-score is different than mu, okay? Let me get this again. I'm going to go back to this. Z-score for individual scores. Z-scores for samples. T is the same as z-score for sample, but we estimated this. Okay. So when we go to this example, and in fact, it's a beautiful example, I think, because you're not given a damn thing here. You're not given anything, but that doesn't mean you don't know what you're doing. I mean, that's the thing. I want to know if there's a difference between celebrity and average Joe. So here's what I'm going to do. I'm going to compare my mean for my celebrity group, my mean for the Joe group. That's the essence. That's the essence of the question, okay? That's why I want you to think about this difference over variability. Here's the question. Here's the question mark. How do we get this variability? How do we get this variability? Okay. And what we're going to do is we're going to get the building blocks. Get the building blocks from our samples. That's going to help us get this value, okay? So I'm going to end here a little bit early because what I want you to do is I want you to get the sum of squares for the average Joe group, okay? And I want you to get the sum of squares for the celebrity group. And then in the next video, we will be looking at what we're going to do with that, okay? We'll look at what to do with those numbers once we get them, okay? We're going to combine them to get a measure of variability. I'm wondering if I should do this. We have time to do this, okay? Well, let's do this. We've done step one, right? I'm sort of fooling around here with step three, but let's do step two. Let's do step two, okay? Save ourselves some time. Step two is setting our alpha level. We're going to continue to set the alpha level at 0.05, okay? So we need a critical t value. We need a critical t value. Now, to get our critical t value, we need to know the degrees of freedom. In this case, and this is going to have to be something that you pay attention to, okay? In this case, what we're going to do is we're going to take the degrees of freedom for the first group, which is what? What's the degrees of freedom for this first group? If there's 6 people in it, the degrees of freedom is 5, yes? Okay. What about for this group? If there's 6 people, the degrees of freedom is 5. We're going to combine these degrees of freedom because we're going to end up combining these sums of squares, okay? So when you have 2 groups, you combined the degrees of freedom for each of the groups, all right? 5 plus 5. Now, the wrong answer would be to say, well, we got 6 people here, 6 people here, that's 12. So wouldn't the degrees of freedom be 12 minus 1 is 11? The answer is no. That is not how you do it. Degrees of freedom for the first group plus degrees of freedom for the second group. So 5 plus 5 is 10. So in this case, We have 10 degrees of freedom. And I'm going to go back to my book. You'll be able to use the your textbook for the final, but you certainly need to know how to use the t-table. So degrees of freedom of 10, I'm going to go across. I'm looking for proportion in two tails combined. So the critical value is plus or minus 2.228. Make sure that you're able to find that, okay? Critical value of 2.228. So when we finally get our t value, in this case, 10 degrees of freedom, when we finally get this value, I'm going to compare that to this critical value up here, okay, 2.228. Notice 2.228 is pretty close to 1.96 because it's analogous, okay? I want this top to be at least twice as big as the bottom, okay? I mean, the more the merrier. If if this is way bigger than this, then you have an even more statistically significant effect. It has to be at least 2 point something. This difference has to be twice the bottom, okay? So I'm going to let you guys do your sum of squares here, okay? Be careful. It's good practice. And then when we come back, I'll show you how to combine the two. Again, this is formula driven. You'll always have the formula for the exam. Two groups. We're going to use a t-test because we weren't given any standard deviation. So get the sum of squares, and then I'll see you for the next video. Stay safe, and hopefully we're progressing to some kind of resolution to all this stuff, and we can get back to some sense of normality. I hope everybody's okay.